Hello, everyone. Thanks all for coming. My name is Qing. I'm a scientist at Los Alamos National Lab. So in this talk, I'm going to introduce DeltaFS, which is a research file system developed at Los Alamos and Carnegie Mellon University. So let's start with a quick discussion on the atomic variables in the C programming language. So atomic variables are variables that are declared with a special type qualifier as shown in the slides. There are many features of atomic variables. One of them is sequential consistency, which means all memory operations happening on a compute node, they form a global ordering. So this ensures that the latest data written to the memory is always used according to this specific global ordering. So this can be very useful when different threads communicate. So for example, we have a thread. Let's say it is going to read some pointer value when a certain condition is met. In that case, we would want that pointer to never return garbage value, and having a global ordering can help us achieve that. So in order to ensure having a global ordering, atomic variables tend to be more expensive to use than non-atomic variables. But fortunately, not all variables of a program needs to be atomic. And in the C programming language, variables are not atomic by default. Applications explicitly request it when needed. Surprising as it may sound, while atomic variables are used as needed in the C programming language, in the file system, this is entirely not the case. So in the file system, all file system metadata operations are effectively atomic, which, for example, files created by one process is going to be immediately visible to all processes, regardless of user need and increasingly prohibit performance penalties. So DeltaFS is designed specifically to handle this issue and to improve performance, and we have some promising results. So in this presentation, let's check it out. So first, just a small number of slides to set up the context. Today, there are basically three forms of distributed file systems. First, we have NFS, which is typically used for implementing home or project directories. In NFS, all clients talk to a single server, and that server tend to be a performance bottleneck. Then we have NASD. NASD is trying to replace that single NFS server with multiple servers. So we have dedicated metadata servers for managing file systems namespace, and we have storage servers for scalable file data access. And today, the Lustre file system, Hadoop, and Ceph file systems all follow this NASD architecture. DeltaFS also belongs here. In addition to these two, we also have cluster file systems. So unlike NASD, in a cluster file system, there is no dedicated metadata managers. And it's basically a bunch of clients running directly on top of some form of shared storage. Those clients tend to know each other, and they run a distributed lock protocol to coordinate access to the shared storage. So for example, when a client wants to access a file in a file system, then another client must first relinquish its lock, flush its memory to the storage, and then so that when the first client go to storage and read the file, it can get the latest data of the file. So cluster file systems are the first to experience global file system synchronization overhead. This is because running a distributed lock protocol across a large number of clients just is going to be very expensive when clients count is high. So today, cluster file systems are usually seen in DB clusters. The cluster size is typically small with no more than 10 clients, for example. So the scale kind of moderate. NASD, on the other hand, is able to support way more clients, way more concurrent clients than cluster file systems. But unfortunately, due to global synchronization, as client count increase, NASD will also see performance bottlenecks. So global global file system synchronization basically means that all file system metadata operations need to form a global ordering. And in NASD, this is basically done by setting all metadata operations to a single dedicated metadata server for processing. So global synchronization ensures fully consistent access across all nodes in the large computing cluster. So those clients may run on different compute nodes, but they act as if they were on a single node. So for example, if a client in this slice, we have application one creates a directory, and application two, regardless of it runs on the cluster, it is able to immediately see the directory and list it. So global synchronization enables distributed applications to simply use the file system to achieve communication, and they can even just use the file system to achieve anonymous synchronization. However, since all metadata operations need to go to a single server, that a single metadata server tend to be a performance bottleneck. So to improve metadata performance, two techniques exist. The first is dynamic namespace partitioning, which allow us to run multiple metadata servers, with each server responsible for one partition of the global file system namespace. The problem here is that potentially lots of dedicated servers are needed if we want ultra high metadata throughput. Another technique is latency hiding, which can be achieved through deep metadata write buffering and LSM trees. However, buffered data eventually needs to be flushed to the server, and LSM trees require compaction to faster read operations. So when those compaction and buffer flush takes place on the dedicated metadata server, and if the server cannot keep up with foreground workload, then those foreground applications will still experience bottlenecks. So DeltaFS trying to attack metadata problems by rethinking first principles. So we basically want to challenge the very necessity of performing global synchronization. So first, not all programs need to read the data produced by all other programs. In particular, unrelated application, they never need to communicate. Second, as cluster size grows, really synchronization of anything global should be avoided. So based on these two observations, we kind of ask, what if we just build a file system that does not require operations to be global serialized? So for example, we have a file system where applications just are able to self-commit their logs, their namespace changes as logs, and store these logs in their shared underlying storage. And then Followup jobs basically just selectively merge logs produced by previous applications for their input. In that case, we don't really have a global namespace, and we don't need any dedicated metadata servers to maintain this global namespace. So again, the idea is that if we have applications simply independently read and write their file system namespace logs, in that case, we don't need dedicated metadata servers to enforce global ordering, and we don't need to worry about our applications being bottlenecked on those metadata servers. So this leads us to develop DeltaFS. So let's check it out. So the DeltaFS is a target for large job running clusters. So DeltaFS applications are expect to be batch jobs submitted to run on large computing platforms. So usually a job is first submitted to some job scheduler queue, and the job waits in the queue for a while. And then it is scheduled, the job reads input, writes its output, and it exits. So this is kind of the basic workflow. And in particular, the input the job reads tend to be static at the time the job is submitted, and output typically is not examined until after the job is done. So this basically enable DeltaFS to implement file system namespace services without performing global file system synchronization for each and every operations. So here is an overview of DeltaFS. So imagine we have compute nodes and a shared underlying object storage. Jobs run on compute node, and DeltaFS is a library code that runs inside each job process. There's no dedicated metadata server in DeltaFS. File system namespace operations are directly handled as log read and write operations. Those logs records namespace mutations and namespace changes, and those logs are basically stored as LS tables in LSM trees in the underlying storage. There is a separate namespace registry service that runs so that the job process can publish its logs to the registry, so that follow-up job can use the registry to recover logs produced by previous applications. There is no dedicated metadata servers in DeltaFS. Instead, the DeltaFS library code running inside each job process serve as file system metadata clients and servers. When a job consists of multiple processes, then each process basically maintain a partition of the job's namespace. Jobs each has its own namespace, and there is no global namespace. The idea is that each job basically runs on top of logs produced by previous jobs to obtain their input, and we don't maintain a global namespace. This ensures that the DeltaFS runs efficiently and does not have any global synchronization. Getting rid of a global namespace enables DeltaFS to have very high single job performance. So to demonstrate that, we did an experiment where we compare DeltaFS with IndexFS. IndexFS is the current state of the art for parallel file system metadata. In IndexFS, all file system metadata operations are immediately serialized in a global IndexFS file system namespace. And due to that, the performance is limited by dedicated metadata servers. DeltaFS, on the other hand, distributes metadata processing across different job processes. So those jobs independently execute file system metadata operations as log operations using the application's own CPU cores. So the performance is not limited by dedicated servers. There are actually no dedicated metadata server. And in the experiments, we can see that DeltaFS delivers up to 98 times faster write performance and about 10 times faster read performance. This experiment is done across 500 client processes. Now let's talk about cross-job data sharing. So previously we've kind of focused on single job performance. So for different jobs that need to see each other's data, we have a producer job that writes something to the storage, and then there are a follow-up consumer job want to read the output of the previous job, and we call this sequential data sharing. And in this case, if there is a global namespace and there is a dedicated server that just immediately serialize all namespace mutations, then this is trivial. The follow-up application can just go to the namespace to find all the data it wants. But for DeltaFS, because there's no dedicated metadata server and there's no global namespace, so DeltaFS require jobs to explicitly specify the logs of previous jobs for input, and then DeltaFS also requires the job to do explicit log compaction to make file system read operations fast. Traditionally, those compaction operations are like executed implicitly by the dedicated metadata server on behalf of all the applications. Here in DeltaFS, the application need to explicitly run it using application's own resources. But the key message we want to deliver here is that even though DeltaFS jobs need to explicitly read and compact logs to enable good read performance, DeltaFS still overall delivers higher performance. So to demonstrate that, we did another experiment where we still compare DeltaFS with IndexFS. We did a 7-stage workflow where each workflow stage will need to see the files created by the previous stage. And each stage will create a bunch of files, and each stage will basically create its own files while requiring seeing the files created by previous workflow stage. So we see that we do this with DeltaFS and IndexFS, and there we show that the experiment shows that DeltaFS is able to speed up performance by reducing workflow execution time by 49 times. And the reason is that for IndexFS, it relies on the dedicated metadata server to execute all metadata operations. But in the DeltaFS case, it can leverage the client compute resources to speed up, to parallelize and speed up metadata operations, and including log compaction. So overall, DeltaFS shows much reduced overall workflow runtime. The true cost of DeltaFS, the true cost of no dedicated metadata server and no global namespace is actually that DeltaFS require more compute resources to execute the same metadata operations. So this is because in DeltaFS, there's no dedicated metadata server. So the clients kind of need to do everything. The clients need to read all the required logs from the underlying storage, do compaction to speed up read operations, and do all the to just execute all the file system queries that needed by the program. While in the normal case, there is a dedicated server, and that server can do everything. Saying DeltaFS, because each job need to do this individually, so there are some portion of the jobs are repeated across the clients. So overall, if we look at an entire workflow across different workflow stage, then overall DeltaFS will consume more compute resources. So in the experiments, we can see that to execute the same workflow, DeltaFS used up to twice the compute resources compared to IndexFS. However, one thing worth mentioning here is that if we change here, our workflow is designed such that each workflow stage need to see the file created by previous stages or previous stages. But if we design the workflow such that all those workflow stages are unrelated, meaning that they do not need to see the files created by previous stage, they only need to see the files created by themselves. In that case, we can see that we call this unrelated job. In that case, we can see that DeltaFS basically use about the same compute resources as the IndexFS case. Another thing we need to point out is that even though DeltaFS requires more compute resources, and DeltaFS requires executing more CPU instructions, those instructions are distributed across all different client processes. So the eventual wartime, the total wartime to execute the workload is not increased. So it's actually much shorter than the DeltaFS case. Another interesting point we want to make here is that while the traditional file system like DeltaFS, it uses less server-side CPU resources to execute automated data operations, but at the same time, it wastes massive client resources by blocking them doing basically nothing. So imagine we have a bunch of clients sending metadata operations to a single dedicated metadata server, and that server is busy, cannot keep up with all those clients. Then those clients will be blocking on that specific metadata operations, and they cannot do nothing, and they cannot do anything, and their compute resources are kind of wasted. Well, in the DeltaFS case, Delta, Delta, DeltaFS is actually utilizing those client resources to process metadata in parallel. So if we count both the client-side resources and the server-side resources, then the overall resource, the DeltaFS actually shows much better overall resource usage. So in the experiments, it's the same experiment as the previous slides. If we count the overall resource usage, then DeltaFS actually improve resource usage by 52 times. So finally, let's discuss what if jobs actually want to use the file system to communicate. Then the answer is simple. DeltaFS simply redirects all those operations to a mechanism outside of the file system, such as a Zookeeper server for synchronization. And the application do that basically by explicitly declare a subdirectory as atomic, and then all those metadata operation happening beneath that directory will go to Zookeeper, and these allow different application to use the file system to communicate. So this is quite similar to C's handling of atomic variables. So basically, if you need it, you just declare a variable to be atomic, and we assume in regular cases, all variables are kind of private, local, doesn't need to form a global ordering. So the key point is that existing file system like treat every metadata operation as atomic, and DeltaFS just want to treat a subset of operation as atomic, and the application just explicitly declare what portion of the namespace need to be atomic. So one example is as we show in the slides, we have two jobs. They want to achieve some exclusive access to some shared data. So they decided that they will do this by creating a log file. So if they see a log file, they kind of will back off, wait until some time and try again. So DeltaFS can redirect this specific log file operation to Zookeeper for global synchronization, while other file system namespace are keep private to different jobs. Okay, so here is a quick conclusion. As cluster size getting bigger and bigger, then if we want to achieve strong scaling, we kind of need some kind of strong decoupling. So existing file system clients simply communicate too often with their metadata servers, and removing those communication kind of force us to rethink what is really necessary and redesign file system accordingly. So the DeltaFS converts file system metadata operations to basically per job log operations, and a job communicate only when it is needed. So we no longer kind of implicitly maintain a global namespace for all jobs, just in case some job process need to communicate with other job process. At exascale and beyond, one size for all solution will continue to lose value. So we kind of need to try radically different model for shared storage. So DeltaFS is one attempt to rethink component communication for distributed metadata, and we expect similar efforts will kind of happening on other areas of computing as well. So that's all the talks. Thanks you for listening. Please check our DeltaFS papers listed in the slides for more information. Thank you for attending. Bye. Bye-bye.